Hi, in this video, we will discuss the topic of angles associated with parallel lines. Let's begin with some standard vocabulary. In this picture here, I've drawn a pair of lines, distinct lines. In this situation, these lines, if you extend them, will intersect. So they're any old pair of blue lines. I've also drawn this red line, cutting pair of lines. This red line is called a transversal. So what we have here is a picture of a pair of lines and a transversal that cuts them. Notice that when we draw such a picture, we form angles which I've labeled here as 1, 2, 3, 4, 5, 6, 7, 8. So one is this angle marked by this arc. I've not marked the other angles by an arc just to keep the picture clean. Now you may measure out angle 1 and angle 3 as an exploratory exercise, and you will notice that they are equal in measure. These two lines intersect and they form 4 angles, and this pair, angle 1 and angle 3, are called opposite angles, and they're equal in measure, and that's what I have written out here. Here is the list of all the opposite pairs of angles. Angle 1 and angle 3, they would be equal in measure. Angle 2 and angle 4, they are equal in measure. Angle 5 and angle 7, that's another pair of opposite angles. They would be equal in measure. 6 and 8, another pair of opposite angles, equal in measure. So the theorem is opposite angles are equal in measure. Let me convince you now why angle 1 and angle 3 are equal in measure. And let's recall rotation about a point by a certain degrees. That's an isometry, and one of our assumptions about the Euclidean plane is that isometries preserve degrees of angles. Let me use a transparency to demonstrate that. So here, as carefully as I can, I'm going to copy this picture and I'll mark out angle 1 and this is angle 3. So I'm now going to look at rotation as a transformation of the plane. So rotation about this point and by 180 degrees. So if I do that, every point in the plane moves except the point of rotation. I'm only going to focus on this angle and see where that moves. So rotation by 180 degrees, and this is what I get. There it is. The angle that used to be angle 3 is now exactly on top of angle 1. So angle 1 and angle 3 are congruent and they're equal in measure. And so what we've shown is when we perform a rotation about this point by 180 degrees, angle 3 lands on top of angle 1. Rotations preserve degrees of angles. That's another way of saying it. And that is why angle 1 equals angle 3. Now let's discuss this term called corresponding angles. So in such a situation, when a pair of lines are cut by a transversal and 4 angles are created here and 4 more angles are created here, we can talk about certain pairs of angles which we call corresponding angles. So let's look at angle 1 and angle 5. Angle 1 and angle 5. So focus on this angle and this angle. They are on the same side of the transversal. In this case, they are on the left side of the transversal. And notice that they are in a same position, meaning angle 1 is above the blue line, angle 5 is above the blue line here. So we call angle 1 and angle 5 angles that are in corresponding positions. For that reason, this pair of angles is called corresponding angles. So similarly, notice 4 and 8 are called corresponding angles. 2 and 6, that pair is corresponding angle pair. 3 and 7 are once again corresponding angles. So keep that in mind. Notice that if you were to draw such a picture where your blue lines are just any old blue lines, they may intersect. And if you draw a transversal like this, notice that if you measured out the angles, angle 1 and angle 5 need not be equal. What if these blue lines were parallel lines? Is there a relationship between corresponding angles? And let's discuss that now. And now let's discuss about angles associated with parallel lines. So in this picture, I have a pair of parallel lines. So unlike in the previous picture, this time the blue lines are actually parallel. And as usual, I have this red line, which is the transversal line. So I have my angles 1, 2, 3, 4, 5, 6, 7, 8. Now that these two lines are parallel, something interesting happens about corresponding angles. Remember, we just discussed corresponding angles. So in this case, you can draw such a picture, measure out these angles using your protractor, and you will notice this angle 1 and angle 5, which are corresponding angles. They're equal in measure. Remember, 1 and 5 are corresponding angles because they're on the same side of the transversal, on the left side, and they are in those corresponding positions. This one is right above the blue line, this is right above the blue line. They're in very similar positions. So 1 and 5 are corresponding angles. If we are told that these blue lines are parallel, they're actually equal in measure. You'll also notice 4 and 8 are corresponding angles, and they're equal in measure, just because these blue lines are parallel. Similar statement about 2 and 6, they're equal in measure. 3 and 7 are equal in measure. So the theorem we have is when parallel lines are cut by a transversal, then the corresponding angles are equal in measure. Now I want to convince you informally using transparencies why this theorem is true. So let's recall that the three basic isometries, translation along a vector, reflection across a line, and rotation about a point by a certain degree, those preserve degrees of angles. So I think to myself, if I want to show that this angle 5 is exactly equal in measure with angle 1, or said another way that angle 5 and angle 1 are congruent, which of those three isometries will help me here? And take a minute to think about that, and then you'll come to this conclusion that if I were to look at this vector I'm going to draw with a green line like this. This is the vector. It lies right on top of the red line. I just drew it slightly away so you can see it. Now what I'm going to do is I'm going to do a translation along that vector. Perhaps you've already figured out what happens when we do that. But let me use this transparency actually and sketch out this picture as carefully as I can. So there's the vector, and I'll also draw the parallel lines. And this transversal. Now let's mark angle 5 and angle 1. And now I'm going to do translation along the green vector. So every point moves, and I would like to see what happens to this angle 5. So there's my translation. What do you notice? Angle 5 landed exactly on top of angle 1, and that shows that angle 1 and angle 5 are congruent, and so they're equal in measure. The same activity that I did, if you observed, also moved angle 6 to angle 2. So when I did the translation along this green vector, angle 6 landed exactly on top of angle 2. So 2 and 6 are congruent, and hence their measures are equal. And so you can now believe why we have these equalities here and why the theorem is true. Now let's look at what I have here. I erased the part that said the blue lines are parallel. So since I have not told you the blue lines are parallel, just think of these two lines as just a pair of lines. We don't know anything other than the fact that they're a pair of lines and that the red line cuts through them like that. So the red line is still a transversal of these pair of lines. And notice that all these angles are formed. Suppose we are given these equalities. Suppose we are told that angle 1 is actually equal to angle 5. In fact, we don't need to have all of the equalities. Suppose we are given one of them. So, for instance, suppose that these two angles we are told are equal in measure. So another way of saying is these corresponding angles, that pair of corresponding angles are equal. Here's a theorem that tells you in that case we can actually conclude that these two lines are parallel. When corresponding angles are equal, then the pair of lines cut by a transversal are parallel. This theorem is called converse of the last theorem that I showed. So how do we believe this theorem? The same activity should convince you. Say we translate along the green vector. Because we are told 1 and 5 are equal in measure, the translation will take this angle exactly on top of that angle. So that means translation along the vector took this blue line right on top of that blue line. Recall that translation maps a line to another line that's parallel to it. So that proves that these two lines are parallel. So summarizing, if we are told this pair of lines are parallel and this is a transversal, then from there the first theorem we did tells us the corresponding angles are equal in measure. Conversely, this theorem, if we are just given any pair of lines and a transversal, and we're given the information that some pair of corresponding angles are equal, so either this information is given or this or this or this, so one of the pieces of information is given, right away then you can conclude these lines must be parallel. So keep these theorems in mind, and more importantly remember how we use translation along a vector to convince ourselves that the theorems are true. In another video we'll continue our discussion about some other angles that are associated with parallel lines. Thank you.